Our third example for taking derivatives. Notice in this example we have a couple different things going on. I'm showing a different notation here. This notation is saying to take the derivative of this expression with respect to x. Also, as you look at the expression, notice that the exponents, all the x terms, are on the bottom, which means that the exponents will all be written as negatives as you bring them up. That's my first step, is to write this in exponential form. And so I look at this and I can write this as negative 3x to the negative fourth plus 4x to the negative second minus 9x to the negative first plus 5/8, where I've brought all the x terms up. As I attempt to take the derivative, I will pay attention that these exponents are all negative. And so in my next line, negative 4 times negative 3 is 12, x to the negative fifth, because you have to subtract 1 from that exponent. So it's negative 4 minus 1, which is negative 5. Negative 2 times 4 is negative 8, x to the negative third for the same reason. Negative 2 minus 1 is negative 3. Negative 1 times negative 9 is positive 9, x to the negative second. And as always, when you take the derivative of a constant, it drops out. On the next line, you'll see that I drop the x terms back down, as you're not allowed to have negative exponents in your answer. So I have 12 over x to the fifth minus 8 over x cubed plus 9 over x squared. One other thing that I can do, I can take all three of these fractions and turn this into one big fraction by finding a common denominator. To do this, I would multiply the middle term by x squared on the top and the bottom, and the last fraction I would multiply top and bottom by x cubed. The result, I would get 12 minus 8x squared plus 9x cubed all over x to the fifth. For some books, this is just a cleaner version for your final answer. And you'll see from problem to problem, I'll ask to write the final answer as one big fraction. This is what I'm referring to. Example 3, taking derivatives using the power rule.